right. Hey, subscribers. Welcome back to another episode of Science with Surback. Today, what we're going to talk about is section 15.1 in our Intro to Chem and Physics class. And this section deals with different types of waves. So, before we get started with this video, there's a few objectives that I want you to be able to accomplish by the end of this section. Number one, determine what a wave carries. Objective number two, know how waves are generated. Objective number three, determine the difference between a transverse wave and a longitudinal wave. And objective number four is determine how particles in ocean waves move. So let's get started with the basic principle of waves. And so waves are defined as the disturbance that carries energy through matter or space. Alright, so again, this is a real general definition of a wave. We'll get a little bit more specific into the end of this section, but a couple of points to make about waves. Number one, this energy moves along the with the wave through its motion. The second point to make here is that no object is going to travel with the wave. And these 2 points will make a little bit more sense when we go through our example here in a few moments. So another thing that we have here is this. Specifically, these things are called mechanical wave. Now, a mechanical wave is just a wave that is going to require a medium through which to travel. And so this medium through which a mechanical wave travels is just matter that it's specifically traveling to. Now, an example of a medium are things as simple as air. That's where sound waves travel through. Water, which you think of a typical wave on the ocean, that's a water wave, or the water is that medium. And then we also have earth. If you think of earthquakes and the movement of earth during that time, the earth is that medium in which the wave is traveling. Now, one last point to make here is that most waves are mechanical waves. However, one major exception is going to be an electromagnetic wave. They do not require a medium to travel through. Again, there is that exception. I know I had to squeeze this in here, but a mechanical wave, most of the time when we talk about waves, they're going to be mechanical waves. Big exception here is electromagnetic waves. And we'll talk more in depth and in detail about electromagnetic waves later on in this chapter. So now we have an idea, now we have a thought process of how we can look at waves and how we can talk about waves in terms of this energy. So we have a simple ocean wave, and what I'm going to draw with my pencil here is going to be a ocean wave. And we have on top is going to be a leaf. Now, I'm no artist, so I'm going to take out this purple pen that I have here, and my leaf here is going to be floating on top. I guess it looks more like a twig, but that's okay. Anyway, so that's my leaf here. Now, as the wave passes, this leaf will bob up and down. So right here, this is our first, it's kind of a snapshot. It's kind of a snapshot in time of what we have going on. So as the wave passes, again, this is an ocean wave, so the medium is the water. As the wave passes, what will happen is this. The energy will move from left to right, in this case here, but that leaf will not move. Now, let me draw this second phase of this picture here. So we let a wave go by, or a half a wave go by, and now what we're going to have is something that looks like this. Now, what happens here is this. This leaf is still in that same exact position. So again, I'll draw my twig leaf here. This leaf is still in that same exact position even after the wave has passed through a whole section. All it's done is it's bobbed up and down. So energy is the only thing that is going to move left to right. In fact, these drops of water that are in the wave are going to stay in that same position as well. That medium, all it's going to do is it's going to bob, or it's going to move up and down, and we are not going to have anything besides energy move. So let me write this down. Let me make a few points out here to the side, and then we'll move on to the next page. So there are those points there. Again, the leaf, it will bob up and down as that wave passes, but it's not going to move left to right in the direction of that wave. Now, energy is the only thing that moves along with that wave. And this will be explained, especially the ocean wave here. It'll be explained a little bit more in depth and in detail as we go along in this particular chapter. So now what we can go through and we can talk about is these electromagnetic waves, which it is also a concept discussed in chemistry. But for us right here, our electromagnetic waves are defined as a wave that consists of oscillating electric and magnetic fields which radiate outward at the speed of light. So I said earlier that an electromagnetic wave was one of the few types of waves that does not require a medium. And to emphasize that point, or to answer the question why that is, well, what happens is that these electromagnetic waves, what they're doing is they're transferring energy by changing the electric and magnetic fields in space. So because they're changing the electric and magnetic fields, those are things that you just can't reach out and grab. They're there, and so that's why electromagnetic radiation can go from one point to another, but it's not something like water where you can actually physically touch that and grab it. It's not consistent of something along the lines of matter. It's not. So some examples of our electromagnetic radiation include light traveling from the sun, our sun, to Earth across empty space. Oh, yep, and I made just a minor mistake here. I already had a space for my examples here. But again, the first one here is light traveling from sun, our sun, to Earth across empty space. Another example that we have are simply radio waves. Now, both of these examples are really good at wrapping our minds around of we can't reach out and touch this electromagnetic radiation or electromagnetic waves. You feel the energy from the sun when you go out on a warm, sunny day. And same thing with radio waves. You can hear that sound on the radio, but it's not like you can just physically jump up there and grab that particular type of electromagnetic wave. You just can't. And it's because they are doing this odd thing here where they're transferring energy via that electric and magnetic fields. So let's get in depth and let's get in detail talking specifically about the energy of these waves. We've talked about it, but we haven't discussed the details here. So with our energy from our waves, what happens is this: waves carry energy because they have the ability to do work. So the key thing here is that waves have the ability to do work, which, remember, that ability to do work, when we talked about that in terms of energy, now we can start making some both quantitative analysis on this business of the waves, and we can actually see, well, what happens as a wave moves from one point to another. Well, now we can associate that energy because it has this ability to do work. And so to give you some ideas about this, I have two examples. The first example is this: water, a simple water wave, or a wave moving through water, it has the ability to do work, those water waves, by moving an object up or down, such as a boat. And again, you can think of that object as a boat. If you've ever been out on the lake or the ocean and you have that wave come by, you feel that rocking, that up and down movement, and that's because that wave that is moving through the medium of water is doing work on the boat by causing that object to move up or down. Now, the other example here is this: sound waves are going to do work by vibrating your eardrums inside of your head there. Now, those are both examples of mechanical waves. One example of an electromagnetic wave would be the sun. If you go out on a hot, sunny summer day and you don't wear sunscreen, that sun, the radiation from the sun, the energy it's going to have is the ability to produce that sunburn, and that energy is doing work on your skin by producing that sunburn that you would obtain by going out on the warm sunny day without any sunscreen. The other main point that I want to make here with the energy of the waves here is that the energy of the wave is directly correlated to the wave size. So simply put here, the bigger the wave, the greater the energy. And then the last point I want to make here about the energy of the waves is that as a wave moves from point A to point B, the energy of that wave is going to spread out. So what's specifically happening with that energy as it moves, as a wave moves from one point to another, is the wave, the energy itself, is spreading out over a larger area. And the best way to think about this is dropping a rock into a pond or a body of water. Well, what happens initially, you get those big ripples right there where you drop the rock. And then as that wave moves further and further out away from where the rock was originally dropped, what happens, and you can see it, those waves get smaller and smaller and smaller, and that's because that same amount of energy is spreading out over a larger area. The other point that I want to make here is that as an energy or as a wave is spreading outward, what happens are those wave fronts, and these things are the circles that the waves travel in. That's what those wave fronts are. They're getting bigger and bigger and bigger. Again, think of that dropping a rock into a body of water. That wave front, the whole area that wave is covering, is getting a lot larger. So again, as a wave moves from one point to another, it's spreading out over a larger area, which means the energy is spreading out, and specifically here, these wave fronts, these circle patterns or these circles that the waves travel in, are getting bigger and bigger and bigger. So now what I want to shift gears into is this: the parts of a wave. And it's important here to visualize what we have. So I'll change the pages and we'll get started with that. Okay, so with this picture of our wave, now one thing, this is our standard transverse wave. We also have another type of wave called longitudinal wave, which we'll talk about here in a little bit. But I want to go over the basic parts of a particular wave with this, again, transverse wave. There is another version, and we'll talk about it here in a second. But the first thing that I want to talk to you is this item right here at the very, very peak. And this is called the crest of the wave. Now, over here, right where my pencil is at, that is also another crest. And then the bottom portion is going to be the trough. Now, again, that trough repeats itself over here on the right hand side. Now, we are going to go in section 2, we're going to go in a little bit more detail about the specific definitions of each of these things. This is just outlining where these items are. Now, the other thing that we have to discuss is the amplitude or the height. And so imagine this. Imagine cutting the wave directly in half from left to right. So what I'm going to do is I'm going to draw a dotted line. And so the space from the dotted line here to the crest, this is the amplitude of a particular wave. Now, when we get into the definition here, again, it's from the origin to the top of the wave, but it can also be the origin to the trough of the wave. So those terms can be used interchangeably. And then we have our wavelength. And our wavelength can be defined in terms of two things here. The first thing is this. A wavelength can be defined as the distance between two crests, or it can also be the distance between two troughs. Now, length should be the same. All right, so now talking about two things, and I am going to go through the definitions here of these two things because it's hard to visualize on this particular sheet of paper. The first thing that I want to talk about is what we call the period of the wave. And so the period of the wave is defined as the time that it takes a complete cycle or wave oscillation to occur. So if I had a stopwatch and immediately when one crest went by, I started that stopwatch and then I stopped the stopwatch at the same point where I started, that would be the period. Now, the frequency, on the other hand, is the number of cycles or vibrations per unit of time. So in this case with frequency, what I'm going to do is I'm going to start the stopwatch and I'm going to let it go by for a designated period of time, let's say a second. And I'm going to then determine how many total wave cycles went through in that particular designated time. So period, I go wave to wave, how long does it take? Frequency, I choose the time, and then on the flip side, I count how many wave cycles go through. Now, like I said, this picture right here is of a transverse wave. We will draw this again, and then we'll also talk about a longitudinal wave here in a few moments. But now before we get into those details, let's get into a little bit of detail on how a wave moves. I mentioned on the other page that they are going to move through those vibrations. And if you can kind of imagine that up and down motion that occurs as the wave goes through some medium or the electromagnetic radiation as it oscillates between those electric and magnetic fields. Either way, it is producing a wave which has those vibrations. So, number one, vibrations are related to waves and vice versa. Number two, the majority of waves are caused by vibrating objects. So those are those 2 points there. The best example to understand this is through sound wave. So what's happening here is this. As I talk and this video records, and it records what I'm saying, I am talking, which is vibrating my vocal cords, that is producing a sound wave that vibrates the microphone, and then when you listen to this video, the vibrations come out of your speakers and hit your eardrums, which vibrate, and you hear it as sound. And we'll get into more details in the coming chapters about the specifics of sound waves, but that's generally how it works. Now, again, we talked about electromagnetic waves. They are vibrating those charged particles, which are the electromagnetic and the electric field. And then the mechanical waves. Think of an earthquake, right? The ground is shaking. The earth is moving. It's vibrating because of that energy produced during that wave. Now what we get into is a little bit different thinking here. So I'm going to give you the definitions, and then I'm going to draw the picture the best I can. So simple harmonic motion is defined as a vibration or oscillation that moves an object and exerts a force proportional and opposite of the original displacement force. So the best way to think about this is through a picture. So what I'm going to draw is this. We have a mass which is on this spring, and I'm going to draw, here's my spring, and it's attached to a mass. That's that square object there. Now, imagine pulling that mass down. It's a spring, so it will come down a little bit. And so as you pull this down, what you are going to do is you're going to stretch out that spring a little bit, and that mass is going to hang down right here at the bottom. Now, as you release it, what is going to happen is that spring, which we can simulate this as a wave, is going to scrunch up. It's going to utilize that energy, and it's going to move this mass or move this weight that's attached to it all the way up there. So the spring right here is compressed. Now, as this kinetic energy turned into potential energy, we again have this opposite and proportional force. So the fourth picture that I'm going to draw here is that the spring is going to come back to its original position there that we drew in our first picture. And then as this continues, the kinetic energy is going to allow the spring to pull this down all the way to that maximum stretched out position. So again, we stretch out our spring and then we attach it here. So imagine our simple harmonic motion as this up and down bouncing that we get, and that up and down bouncing is equal and opposite that original force. Just one way the vibrations of a wave can move. Now, we get over to this definition here, damped harmonic motion. And what damped harmonic motion is defined as a vibration that dissipates out as energy is transferred from object to another, or from one object to another. Now, simply put, what happens here in the damped harmonic motion is that the amplitudes of those oscillations, so those vibrations, are going to decrease over time. And so the best way to see this is through an example here. And this is really best done in the lab. But again, what I do here, I'm just going to draw a board. Imagine that we have a board, and connected to this board are going to be a series of weights that are attached to the spring via the board. And I'm going to draw, I don't know, 3 or 4 of them here. And so I have another weight and a third weight. And then let's draw a 4th weight. And so what I'm going to do is this. I'm going to attach all 4 of these weights from one weight to another with another connected spring. So all of these things, all of these weights on springs are going to be connected together. And so what happens is as I pull this weight down, originally as I let it go, it went up and down and up and down. But now, because these things are connected together, what happens is as I pull down on this first weight and I let it go, what happens is that some of that energy is transferred not just up and down to make this first spring go up and down, but also in this connected spring. So we have a little bit of energy going up and down, and some of that energy is transferred in this spring from left to right to make this one go up and down, and that is transferred to this this next connected energy, and this one makes it go up and down, and so on and so forth. Now, as that happens, because my energy is being displaced into 2 different ways, up and down and side to side, what happens is that energy won't last as long. You won't get as high of a bounce back in your weights on a spring. So the point of this picture is that the height or the amplitude is decreased. Again, this is a lot better seen in a specific example. Now, also what we have to think about, we go back to that original example I gave with the leaf, and we talk about our picture of our wave. And so a key thing here, as a wave moves, particles are vibrated in a similar way that we have these connected masses. So they really model this damped harmonic motion. And so what we have is this. I'm going to use a couple different colors. And we're going to start out here, and let's pretend that I have a yellow rope or yellow string, and I attach it right here. Now, also imagine that I have a rope that is connected to like a door or a doorknob, and I'm going to move that rope up and down. And we've probably all done this or seen this. And now as the rope moves up or down, the energy is transferred from left to right, and then the other thing is this particle is going to move up and down. Now, the particle does not change positions, and so this is why I use this colored pin here, is as the wave moves up and down, as it moves up and down, what happens is the particle stays in that same location, and our energy is transferred in 2 positions. One, it's going to transfer energy up and down as this particular rope is thrown up in the air and tossed back down. It's going to transfer that energy up and down, and then the energy to get this movement, this nice transverse wave, we have to have side to side, or in this case left to right movement. So there's 2 types of energies that are occurring here. Now, to emphasize this once again, if we had another string attached to this particular rope, the strings, that location does not change left to right, but as the wave passes, it is going to move up and down. And so that's what these particular different colors are representing. As I move up and down, or as the wave passes, the particles of the wave move up and down, but the wave overall moves left to right. Now, the energy is transferred both up and down and left to right. So let me make a few notes here so that we can summarize what is happening in this particular picture. So there's that point here. I know it's squeezed in there, but waves energy is transferred up and down. You saw with the movement of these ribbons or these yarn tied around a rope, and the wave moves left to right. Now, an important thing, the reason that we learned about this motion is this. This picture of a wave where we tied a rope to a doorknob and we moved it up and down is really similar to the movement found in damped harmonic motion. So let me make that point. So again, there's that point. This energy transfer in a wave, a transverse wave that is very, very similar to that energy transfer that occurred in that damped harmonic motion. Okay, so we have an idea of the energy involved in waves, how they're moving specifically in those vibrations or what we call oscillations. And now our final part, our introduction to our waves, is we can talk about the different types of waves. So in this class, we are going to talk about 3 different basic waves. And so the 3 different waves are transverse, longitudinal, and surface waves. Now, so what I want to do is go through each of these types in detail. I want to give you the definition, the basic gist of what happens, and then a picture as well. So we start out here with a transverse wave. Now, a transverse wave is just defined as a wave in which the particles of the medium move perpendicular to the direction the wave is traveling. So what we have with a transverse wave is something similar that we've seen, and we have that up and down motion, or the motion is perpendicular to the particle motion. So a couple of examples of this include electromagnetic radiation. And another example is that rope tied to a doorknob, similar to that picture we went over in the previous page. You had that up and down movement of that particular rope tied to a doorknob. And so to give you an idea of a transverse wave, we've gone over it before, but a transverse wave is going to look like this. And now the tops are called the crest and the bottoms are called the trough. A point from trough to trough or from crest to crest is what we call a wavelength. Now, a longitudinal wave, I've mentioned it, but I haven't gone in much detail. A longitudinal wave is just defined as a wave in which the particles of the medium vibrate parallel to the direction of travel in which that wave is moving. Again, the key word here for longitudinal wave is that parallel. There's that parallel movement of the energy and the wave motion. Now, a great example of this is going to be pushing a slinky back and forth. So I'm just going to simply put a slinky. Now, as you move the slinky, imagine if I had a slinky right in my hands and I started to move it from one end, or I pushed it from one end or the other. What happens is it almost seems like the slinky is moving in a snake-like pattern, and I'm getting a basically a spring to compress and what we call rarefaction move in those motions here. So let's draw a picture of this and I can explain what we have. So as we have this slinky, it is going to be pushed together. So the spring of a slinky is going to be pushed pretty close together, and then it's going to widen out. So if you can't tell from this picture here, is as it moves from one place to another, it squeezes, or we call that the compression, and then it stretches out, or we call this the rarefaction. Now, as it goes from one to another, it's going to go from that squished version to that lengthened out version. So what I'm going to draw here is that compression, and then once again, it is going to stretch out, and this movement of the wave simulate that particular particles. Now, one thing I do want to hit here is this portion right here, where the portion of our slinky is squeezed together. This right here is called a compression. And then the portion where that slinky is stretched out, this is called the rarefaction. And we will get into more details later on in this chapter, specifically about longitudinal waves. So that is how a longitudinal waves, again, think of slinky. As I push a slinky back and forth, you see that movement of the springs, and that's what I'm trying to simulate here in this particular picture. Now, our last type of wave is known as a surface wave. And now a surface wave, what happens in a surface wave is this. The particles move both perpendicularly and parallel to the direction in which the wave travels. Essentially what we have with a surface wave is a combination of a transverse and longitudinal wave. And then the other thing that we have to have in order to have a surface wave is this has to occur at the boundary between two different mediums. And so an example of those two different mediums would be something like water and air. So what we also have here with surface waves is the particles. How they are going to move is essentially in an ellipse pattern. So the best way to explain this is through an example where we have the movement of a beach ball on an ocean wave. And so what we have here, what I'm going to do is draw this as a picture. So we're going to draw a series of pictures, and what we're going to have here is our first snapshot or our first picture. And so what we are going to have is this. We have our ocean wave, I kind of exaggerated it, and then we also have our beach ball. And so what happens is this. This ocean wave, and maybe I should make this a little bit more round here. Oh yeah, that's better. So what happens is this. As the ball is in the trough here, and as the crest approaches, remember the ocean wave here is moving left to right. And so as this happens, as this crest right here approaches, what is going to happen is the ball is going to move to the left and upward. So our second picture is this. The ball we have that same wave here. The ball does this. The ball is going to move in a shape that's like this of my arrow. So again, what happens here is between the first and second picture, the ball moves to the left and upward. Now, as the ball moves to the left, this is the parallel motion of the particular wave, and that's really associated with that longitudinal movement. And then that up and down motion is it moving perpendicularly, which is associated with that movement of a transverse wave. And whoop, made a misspelling here. Perpendicular motion. Parallel, longitudinal, perpendicular motion is going to be that of a transverse wave. Now, the third picture that I'm going to draw is this. As it gets near the top, so the third picture here is we now have the beach ball. Maybe I should give myself some room. We now have the beach ball at the top or approaching the top. What happens is this. As it hits near the crest, it starts to move to the right. So what happens is you get a motion similar to what I am drawing on that arrow. So we have this upward motion here. Now we get this circling around motion here as it nears the top. So again, as the ball nears the crest, it starts to move to the right. So as the crest passes, what happens to that beach ball is this. We now have the crest that is passed, and our fourth picture would look like this. The ball is going to start to fall down, and it's going to continue to move in a similar motion of that arrow that I draw. And this is our fourth picture here. So what happens here again is once the crest passes, the ball starts to fall back downward and to the left. And so this makes a little bit more sense when I draw this fifth and final picture, which is really similar. It's actually the same as what we started with. Now, again, the ball is still falling downward and to that left, and then that cycle is going to start all over again. The ball moves up the crest of the next wave and to the left, then it reaches the crest and starts to go downward and to the right, and then it falls down again and moves up and to the left. If you combine all of these movements of these 5 pictures, you get an elliptical pattern, or the ball moves in an elliptical pattern. Whoop. So that ball moves in an ellipse. All right, so we packed a lot of information into this particular video. There's a lot more to come in terms of waves, but as always, I hope you have enjoyed this video, and don't forget to subscribe.